All right, let's continue on Science 30. We're on our Unit B, the chemistry unit. I think we're at 1.2, and this is my second video on this. So continuing where we left off. So some limitations to the Arrhenius theory. There are some compounds that have basic properties but do not have OH ions. So when we can't just generalize bases to always just have an OH, because there is some bases, some exceptions to that rule, that they have basic properties but don't have those OH ions to give off. So those examples are ammonia, sodium carbonate, and aluminum chloride. So it says this theory that has hydrogen ions existing all alone, but this cannot happen. So hydrogen ions have a very strong positive charge that causes it to combine with water to form something called hydronium. So H3O, not H2O. So we're just adding a hydrogen ion onto the water molecule. This is what we believe now causes something to be acidic. So this really doesn't change our definition of an acid because we still needed to have hydrogen in the first place. It's just that we, I guess, simplified it in that theory where we just basically said that hydrogen ions were left by themselves. And we know that's not the case. So when we have an H2O and hydrochloric acid, that's happening here, we would have this hydrogen sort of go with that to make H3O and chloride on its own. Okay, so that's what happens. I guess before we would have just simplified that hydrogen went on its own, but it actually combines with water. That's all it's trying to tell you here. So Bronsted-Lowry theory about acids and bases. It says these two characters, Bronsted and Lowry didn't like that Arrhenius theory had limitations. So they wanted to understand the reason behind the limitations. So these Bronsted and Lowry guys, they came up with sort of some other ideas building off of the Arrhenius acid-base ideas. So some vocabulary we need to know is acid-base, conjugate acid, and conjugate base. So an acid is a substance that donates or loses hydrogen ions. So if you're an acid in this reaction, that means that you lose hydrogen ions. And if you are a base, you accept or gain hydrogen ions, okay? So conjugate acids, these are acids that form when a base accepts a hydrogen ion. So basically it's on the other side of the reaction, and it's the base that gets the hydrogen to become an acid. Then a conjugate base is the base that's formed when it loses a hydrogen ion, okay? And this will become, I guess, easier when we look at an example, which we can do right here. So it says, I guess I should read this. It says, according to this theory, during an acid-base reaction, a hydrogen is transferred from the acid to a base. All right, so basically what we need to do, or how we do these types of questions, is we literally just need to look at the question and figure out acid, base, conjugate base. So acids and bases are always going to be on the left-hand side. So we basically need to look at these two things on the left-hand side, figure out which one's the acid and which one's the base. By looking at this, we can tell, basically, just by the fact that we've got something that's got a hydrogen ion, and we've got an OH here. Okay, but I'm not going to use that as my way of figuring it out because there is those exceptions to the rule? Well, maybe not, but I'm just going to explain it in a little bit different way. So we basically have to look at from one side to the other, sort of like something we did in Science 20 with half reactions, where we need to look at what does this HF become, all right? And that's becoming that, and then this must be becoming this. So we're looking at these things. We need to sort of figure out, like, well, from one side to the other, what are the ones that are the same, and what are they changing into? Then we can see from one side to the other that, see how this is an HF, and on the other side it's just an F. So from one side to the other, it lost a hydrogen. And remember, if we look at an acid is a substance that donates or loses the hydrogen. So from the left to the right, it lost a hydrogen. So we can for sure say that that's an acid. All right. When it loses the hydrogen, it becomes just F. And what we call that is not the base, but the conjugate base. And I'm just going to name it CB. Okay. So when what the acid turns into is called a conjugate base. Now we can look at the other one, and we've got OH, and if we go to the other side, it becomes H2O. All right, so if we break down H2O, that's just basically HOH, right? It's just having an extra H on there. There's two H's and one O. So this, from one side to the other, it gained an H, right? OH is just one O, one H. H2O is two H's and one O. So from this side, this is our base. And when it moves to the other side, that becomes our acid, right? So that's called our conjugate acid, all right? It's the one that gained the hydrogen ion. If you looked at this question without doing that the way I did, you'd probably already be able to figure that out, because you'd be like, oh, this has a hydrogen ion? That must be the acid. And then if you looked at the other side, this doesn't have a hydrogen. This does. That's probably the acid. Then if we look at the other ones, this one is an OH. We always know OHs are bases. And this doesn't have a hydrogen, so that must be the base. Okay, so we can probably figure it out without doing it the way I did it, but this is how you can always sort of figure it out, and that's where that process is coming from, okay? So your acid from one side turns to your conjugate base, and then your base from the right-hand side becomes your conjugate acid. All right. This is in your data booklet. It's the relative strengths of selected acids and bases. And basically it's just showing you that they actually show you in this table what the conjugate base is to an acid. So if our acid is H3O on one side, then the conjugate base would be H2O. So it's giving you a table of what the acid and conjugate base formulas are. All right, and this is something that, it might be useful, but you can probably figure it out when you're doing a question. But let's look at this. So it's a sour gas, contains hydrogen sulfide, H2S. Hydrogen sulfide can dissolve and react with water in the atmosphere. Write the chemical equation of the reaction between aqueous hydrogen sulfide and water. So I guess this is the reason why we need this table, and maybe this is why I forgot about this key information. If we're looking at H2S and H2O, basically if those two things are reacting together, we might not be able to look at that right away and figure out, okay, which one is the acid, which one's the base, because they both have hydrogen ions. But we're going to locate them on the table. And then you want the strongest acid, so the one that appears higher on the table. So we know that H2S is the acid and H2O is the base, okay? So I guess that's what they're showing us here. So just to refresh that, what's going on here? We're looking for H2S and H2O. So H2S is right here, H2O is right here. So I guess whatever one is higher up on that table, that's going to be your acid in your formula, okay? So that helps us to figure out what the other side of the reaction is, okay? So write the reactant side of the chemical equation. So I'm going to do that right here. So we've got H2S and H2O. This is telling us by looking at the table that we figured out this is our acid and this is our base, okay? So now that we know that, we can write the other side of the formula basically by figuring out or knowing that if you're an acid on one side, you change over to a conjugate base. And by doing that, you lose a hydrogen. So H2S, it loses one hydrogen to be HS, right? So when it loses a hydrogen, it's not balanced anymore, so it has a negative charge. If you don't understand that, remember that hydrogens are plus charge, S is -2. So to balance that out, we need 2 hydrogens to keep it at +2, -2. So if we take away one of the hydrogens, then we're left with a negative charge because we've got one more negative than positive. All right. So that's our conjugate base, and then our base will become our conjugate acid, okay? So if you become the conjugate acid, you gain a hydrogen, right? This acid lost a hydrogen. Where does it go? It goes to this base. So H2O would become H3O. Okay? And that is how you do that. Okay, I skipped a lot of steps here. Well, we already did them. We identify the conjugate forms of the acids and bases, and then we write the forms on the product side of the chemical equation. I guess you can probably find them on this sheet. Yeah, it tells you right here. So I guess we didn't need to do it the way I did. You could be like, okay, this is the acid, this is the base form, this is our base, and then this is our acid. That doesn't work for there. Do we have H3O on this? Oh, it's right here. I guess. So we know that the water was our base, so this would be our acid. Okay? So it is on the sheet. I just picked the wrong version. Okay? But again, we didn't need that table. We only needed that table to figure out which one was the acid and the base. And then as long as you're following the ideas that acids always lose a hydrogen and bases always gain, then you can figure out the right-hand side of the equation. Okay? It says the hydrofluoric acid, HF, can be neutralized by a reaction with hydroxide ions of aqueous sodium hydroxide. Write the chemical equation for this neutralization reaction. I don't know where we're going to write this, I guess to the side here. So it's saying hydrofluoric acid, HF, can be neutralized by the reaction with hydroxide ions in sodium hydroxide. So sodium hydroxide. And when we're writing these types of reactions, I'm going to say it doesn't really matter. The sodium has nothing to do with it, so we don't need to worry about it. We just need to focus on the acids and the bases, okay? So, again, we got to look at HF and OH on here and see which one's higher up on the table. But but it already sort of told us in the reaction, and we probably already know that HF is the acid and OH is the base, but just to show it on here, we got that one there and that one there. Okay. So this is our acid. This is our base. So from one side to the other, our HF, it always loses, right? It's an acid, so it loses. So it just becomes F. Where does that H go? It goes to OH. So OH becomes H2O. Right? So this hydrogen joins this on this side of the equation. Okay? This F doesn't have anything, and it goes from there to there on this side. Okay? So our F on this side, it goes from HF to F. This becomes our conjugate base, and our base becomes our conjugate acid. Okay? So Arrhenius' theory could not explain bases like sodium carbonate. Well, Bronsted-Lowry can write a chemical equation for the carbonate ion and water. So carbonate, where do we got it? I guess that's talking about carbonic acid. So if we're going to write this, we've got our carbonate and water. That's what it's trying to give us. So we want CO3 2 plus water. So in this case, we don't have any hydrogens here, so this is going to be our base. This is going to be our acid. What is that going to become? Well, our acid, we'll do our acid first because that's normally what I do. So our acid from this side to this side loses, so that's going to be OH, right? And who gains it? The CO3, so that's going to become HCO3 negative. Let's write that a bit better. So we've got water and we've got carbonate ion. We already said this was our acid and this is our base. Our acid is always losing, so H2O becomes OH, which is our conjugate base. Plus our base goes from being CO3 and it gains that hydrogen. So it has a hydrogen CO3. Because hydrogen has a +1 charge and this has a -2, the overall charge changes to -1. Or just negative. Okay? And this would become our conjugate acid. Okay? So the Arrhenius would be like, okay, only OH things are bases, and when we're using this theory, we can say, well, this can also be a base. So things that are, as long as they are gaining or losing hydrogens, they can be added into these Bronsted-Lowry equations. Okay, so after doing that, there is some examples or some practice problems for you to do there, and they should be in your work booklet.